In this video, we will demonstrate how we synthesize amino pyrite from pictogram dehalogenation and how we set up the reaction in alternating current mode. So for that, we taken first pictogram and we measured around 100 milligram for that, and we will now add the electrolyte, which is 2% sodium hydroxide, into it. So we will measure 2% sodium hydroxide into it, and some 13 ml of sodium hydroxide solution was added. So we measured 13 ml of sodium hydroxide solution and added into it. And after that, we just shake it to make it dissolve. So as you can see, it getting dissolved very easily because it is a basic solution. And if something is not dissolved, we can put a stirrer bar and we put it on stirring so that it get dissolved. And when it is completely dissolved, we will use two identical silver electrode for this reaction. So these are the cathode and these are the anode, because we are using alternating current mode. So the cathode and anode are same for this reaction. So now we set up the reaction when it is dissolved. So we put the cathode and anode into the reaction mixture. So when it is dipped in the solution and it is not touching, we are sure, we just connect cathode to the working electrode and anode to the reference and the counter electrode, because it is a 2 electrode setup. So we connect reference and counter electrode together. So after we connect it, we set up the potentiostat for it and run the reaction for 16 hours. For our AC reaction, we will use chronocalorimetry method in potentiostat. So first we will set the method as chronocalorimetry here, and then the initial voltage should be plus 1.8 volt because our amplitude is 1.8 volt. So we first give 1.8 volt to activate the electrode, and then we continue the reaction up to minus 1.8 volt. So it will oscillate between plus 1.8 volt to 1.8 volt during the reaction time, and the number of steps will be 320, which is the highest we can give it in this program, and the pulse width will be 100 seconds, which is equivalent to 5 millihertz, which is used in the reaction. And with this parameter, we will continue to run this reaction for 16 hours. So in between, we have to also restart the program, because this program we can run only for 8 hours maximum. So we just run the reaction by clicking the play button, and we will have to wait for 16 hours. The reaction was started, and after 16 hours, we will analyze the products. After the 16 hours, we can see the reaction is now over, and we can see change of color here. And so for the further workup and determination of the molecule concentration, we first disconnect the electrodes and then take 0.5 ml of solution from the reaction mixture. And as it is a very highly basic solution, so we first need to use dilute HCl to neutralize it. So we added 0.5 ml of dilute HCl to neutralize it, and you can see the color change as it gets neutralized. And then we add 1 ml of ethyl acetate to the reaction mixture so that we can do the workup. So after mixing ethyl acetate, we just close the vial and shake the reaction so that the partition was efficient. And you can see the partition was done. So the top part is the ethyl acetate and the bottom part is our reaction mixture, and most of the reactant and the product should come to the ethyl acetate part. And then we add some internal standard for the GC analysis. So we add a 20 microliter of the internal standard to it, and we again shake up the reaction mixture, and it will again partition between the water part and the organic part, and the organic part should have the product and the starting material. So after that, we will take up some amount of the organic part and do the GC analysis. So in the GC analysis, first we have to load the correct method for this reaction. So we have already designed the method for this reaction. So first we will load that, and then we will go to instrument parameters where we can see all the different parameters for this method. So if we go to the instrument parameters, we can see this is the temperature program which we are using and which is also mentioned in the supporting information of our manuscript. And then when this method is loaded, we will run the file. So we have to give a certain name for the reaction. So we'll give a name and click open. So we will giving a name of AC1 here and just OK. And then it will ask for, as it is a manual injection instrument, it will ask for injection. So then we have to load the sample in a syringe, and we have to inject the sample and as well as click the start button here. So as soon as we click the start button here, the measurement will start. So as the GC instrument is running, we can see several peaks as it is forming. So initial peaks are of solvent and we can ignore that, and our original peaks will come from around retention time of around 9 minutes, where we first see the internal standard peak. So these peaks which are appearing here are mostly comes from the solvent, so we can ignore here, and we will see from retention time 9 how the peak is going to form. So you can see here, as the retention time approaches to 9, it will show a peak at around 9 minute retention time, which we previously determined that it is of our internal standard, which is chlorofluorocarbon, which we mixed in the reaction mixture. So this peak at around 9.1 minute retention time comes from our internal standard chlorofluorocarbon. As the reaction was running, we could see very small peaks which are appearing at around 12 minute and 14 minute retention time, which comes from our other products which are deaminated products which are forming in the reaction. As in the AC mode, the rate of formation of our other deaminated product was very less, so we could see very small peaks at 12 minute, 14 minute and 16 minute of retention time. And after around 17 minutes, we could see a big peak is forming, which we determined previously that it was the peak of aminopyrite by injecting the original aminopyrite molecule. And also we could see there was a peak around 18 minute retention time, which we previously also determined comes from the picloram molecule. So by comparing the area under the curve of these peaks, we could determine the concentration of the molecules in the reaction mixture, which was discussed in the supporting information of our manuscript. So from there we could quantitatively measure how much aminopyrite is forming in the reaction mixture.